This video is brought to you by Hackaromo Chalk. Use code TPSA 10% off to get a discount.
Guys, sorry for the delay. We've had some technical issues, but I think we'll get started now. First of all, thank you everybody for showing up to our first staff talk of the year. Today, Professor Kulaxizi has kindly agreed to talk to us about what quantum theory teaches about gravity. So yeah, we'll just get started now.
Okay, thank you. Thank you. Okay. Thank you for your kindness and for coming up. Unfortunately, the audience is mixed, so I have to say, I've prepared a talk that's mostly for second years and third years, and so there'll be a little bit for fourth years. So it's a little bit complicated to work it out for everybody, to be interesting for everybody in a sense. So basically, what will be, what is my research focused on? So it's basically what is, I would say, most of the department's research focused on. So it's both on quantum field theory and gravity, and in generally understanding also the relationship between these two descriptions, mathematical descriptions of the world that we have. So maybe you haven't, some of you, those that haven't gone to the fourth year, haven't seen already like quantum field theory, but you can understand it as those in third year as an extension of quantum mechanics in a sense that allows you to basically, in a certain way, in a certain precise way, study the smallest constituents that we have in the universe, and it gives a pretty correct description of physics to very high accuracy. So we also talked about, besides quantum field theory, that we're interested in gravity. And when we talk about gravity, we mostly think of it in terms of classical gravity. And so what does that do for us? It allows us to study like on the things on the other end of the spectrum of scale, so like very, very large objects, very massive objects, astrophysical objects, and it gives a pretty good description of those. So in a sense, quantum field theory is the mathematics. We can crudely distinguish them by saying that in the quantum field theory would be the mathematical language that we need to describe matter in the universe at very, very high energies and very, very tiny, tiny distances. And classical gravity will be a good mathematical description of the geometry of space and time, and for objects in very, very large distances. So what am I going to discuss or try to say a few things about in this talk is how, in which ways we understand or we can describe in current research the gravitational theory and classical gravity included, but also quantum gravity as well, as an emergent description of physics. So an effective macroscopic, remember we talked about large and massive objects description, coming from distinct microscopic, very small constituents, degrees of freedom. So the outline of the talk is we'll try to understand what did I actually say, okay? What do I mean by an emergent description? And in trying to see this, we'll go through the historical trajectory of some of these ideas. Then we will discuss the concrete realization that maybe some of you have heard of that, which is what is sometimes called holographic correspondence or NDSCT correspondence, or any other similar engaged gravity duality. It has all sorts of names. Maybe then we'll discuss about current research. What does it tell us if we use this tool to see how gravity emerges from quantum description? What does it teach us? Okay? And how can we push our understanding further? So let's say a few words about gravity, geometry. So you all probably know the standard classical Newtonian laws of gravity. So this will be like our introduction. So if you have two masses and they're separated by a distance, you can express their Newtonian gravitational force in that sense, where you have a mass capital M and a mass small m attracting each other. So this very, very simple formula in a sense. Of course, together with all the classical understanding of motion and the principles of motion, is good to describe very well, to a very good accuracy. So a good description of the solar system. So probably those of you that are in second year have or are or will be discussing the planetary motions and how they are described by ellipses, where the sun is, so this is the planet, orbiting around the sun, and sun is one of the foci of the ellipse. The ellipse has two foci, and this distance is called the eccentricity of the ellipse. So these pictures you've seen a lot, and all of this is very well described by just these simple motions. So, however, historically, after the great success by Kepler and observations of all these great physicists at the time, there were still eventually some mismatches with observations, and this came about with the famous precession of the perihelion of Mercury. Usually people call maybe this point perihelion and aphelion. Helios in Greek is sun, so peri is close, aphelion comes from apos, it's far further from the sun. And the point was that there was some movement at this point that wasn't described correctly by the equations that would come out from classical Newtonian gravity. And that, let's say, this, and well, unfortunately, the pictures will not be that great. So of course, when you first see something that's not quite fit your predictions, you don't go and throw out all of your theory. You first check whether there's something that you didn't take into account, and if you actually account for it, the theory will correctly describe what you're observing. And that's what initially happened. So what people thought was that probably there is the contribution of other planets which are affecting the motion of Mercury, or perhaps, since after this didn't work out, perhaps there was some other very big massive object that would account for this difference. And that was checked as well, and nothing was found. So the theory that actually gave an answer to this movement of the perihelion of Mercury, it was general relativity. So we said we'll be writing here. So oh, also have music. So general relativity told us that this precession in the change in the orientation of the orbital ellipse was explained by gravitational effects that were related to the curvature of space-time, which is of course associated to the solar system. So it was an effect due to the massive objects that are in the system, but we had to correct our equations, okay, for those, and it actually predicted it pretty well. So why was it seen in Mercury? That was because this planet was closest to the Sun and it had the shortest period. So that was one success of this new theory, general relativity. We didn't say anything about it, we'll say a few words later. What is the other success that now Einstein's classical theory managed to do? It's another classical, many more tests that have been and predictions, and you probably heard a lot of them. So one of them that will somehow play some role in this talk is what is called Shapiro time delay and deflection. So if you have you can actually see it in terms of solar system. If you try to send some light signals to Venus because of the presence of the Sun, there will be some time delay compared to the expected arrival of the signal due to the presence of this very, very big massive object. And there will also be some bend, so this has to do with the time delay, as opposed to the case where the Sun will be there. And that's the delay, and deflection has also to do with the trajectory, the spatial trajectory of the light. So here I'm talking about a very light particle, or a particle that is actually light, so it travels with the speed of light. And maybe we can look at a picture for the bending, let's say, of the deflection, since I don't have the pictures that show you in the slides. So if you have, let's say, a very massive object here, you can see trajectories like this. So due to the attraction that this very massive object does to the particle that passes, say, in this trajectory doesn't go straight, but it bends a little bit, is attracted by the particle. Similar things you can see in the other scattering. Another, but in the opposite direction, because there you have depending on what the charges are, but often you see it in the opposite direction than as opposed to relativity, because you might have instead of attraction repulsion. So, and usually what you would call, what is this called, if this is your massive object and this is your particle that travels in this direction, I shouldn't write C, we assume that it's so small compared to this that basically this could be like a particle that's light itself. It can travel with the speed of light compared to this particle, so it's almost massless. It doesn't have any mass compared to this very, very heavy object. And now obviously this is in terms of the force of the attraction, but that at the same time is also in terms of general relativity, part of the curvature of the space-time that's associated to the presence of this massive object. Okay. So what do we call usually this distance? This distance is called the impact parameter in scattering. And you will tell me what is the scattering here. It is indeed scattering, also it doesn't hit it precisely because it is its trajectory is deviated and clearly affected by the mounted object. So in certain units, you can actually measure the time delay. So here I try to depict the deflection, the time delay that the particle will have compared to its traveling without the presence of a heavy objects, and that could be, roughly speaking, proportional to Newton's constant, the length of the momentum of the particle, and logarithm of b, where b is the impact parameter. Okay, so in some simple units in flat space-time, that's the prediction that we have. Asymptotic flat, far from the massive object. Now, when we're talking about particles, there is a way, I didn't tell you how the deflection looks like, because I'm going to use for later some other quantity. Instead of computing separately the time delay and the deflection that could be measured in terms of an angle, for example, I will consider the particle wave duality, and I would say originally my particle would be described by an exponential, and that's a wave that's passing through, traveling in space or close to this massive object. But then, due to the presence of this massive object, the position is shifted, and therefore here I can write, I can have my original term plus I delta, where delta is called usually the phase shift, exactly what it actually is, okay, and it's related to these changes that are bringing it about. So in reality is the momentum in the time direction times delta t approximately plus the momentum in the y direction of the angular direction. So the energy times the change in time, the time delay plus the angular momentum L times the deflection in the angle, in the spatial angle. So you could, instead of measuring separately the time delay and the angular deflection, you could also measure this shift in the phase of the particle as it moves in the presence of this heavy object. And that's what we might do later. So, okay, so we didn't say anything about general relativity, maybe a few words for those of you that haven't seen it. So you know that some of the important postulates or principles of general relativity, one of them is the equivalence principle, which tells that if you fall freely just by the only from the gravitational interaction, then gravity basically disappears for you, in a sense. And you know that the speed, the highest speed of any particle is the speed of light. The time is again taken in the same, is considered as another coordinate together with the spatial coordinates. And here there is like a more intricate understanding now of the space-time geometry. You can think of space, you don't have to always consider time as limit, although it is one of the coordinates. But in terms of how our mind works, it's easy to think of just space. You can think that the space geometry is a result of the masses of the heavy objects that curve space-time around it, and gravity is basically due to the space-time geometry, or vice versa, the space-time geometry brings gravity. So one important thing about general relativity is that once you have a theory, you can also make some more predictions, perhaps not just explain things that maybe you have seen, and this is something that has been measured. For example, this time delay of a signal, but actually predict the existence of things or phenomena that can take place. And one such prediction was the existence of black holes. So maybe we can just write for you the Einstein's equations, although we'll not do anything with them in this talk. But it's good to keep a little bit this picture in mind. So general relativity of light as a GR predicts black holes. And of course, by now, black holes have also been observed. So another test of general relativity. So if we want to give maybe, so what are these objects? First of all, they're very, very massive objects. And close to where their mass is, say, concentrated, of course, space-time is very, very highly curved, but far from that is almost asymptotically undisturbed. So if your original space is flat, then it will be like, oh, naturally, goes to space very far. So there is like a cartoonish description of black holes by Larry Susskind that I found kind of funny. It's not obviously very precise, but so it thinks of black holes as in the following way. You can have like a pond where you have fish and they are flowing in your pond, but then there is some sort of drain at some point that falls into perhaps the mouth of a shark here, or some, I don't know, rocks or something. So we can make it very dramatic this way, although it could be nothing, but we could be for a moment agnostic to what happens there. But at least it looks to us as if if we fall there, something bad will happen. But what is the difference here? Like here is like we have to set some rules that will be analogous to this pond to the ones that are true for general relativity. So the analogy here is that by rule, this fish cannot swim faster than the speed of sound. Okay, so they can't swim faster. Let's say this is our physics law for this example. So the fish velocity has to be equal to the speed of sound, v sound. Okay. And now here, this is the drain. And this drain hole drains out into those rocks or a shark. Now the flow of the water, becomes faster and faster as you go in. And basically this line here that I have drawn is the line where the flow of the water is equal to the velocity of sound. So what happens is that as our stream is fishing nicely and peacefully, if it gets over this, even if it starts crying out, nobody will hear it. Unfortunately, to come to save it. So this is like a cartoonish picture of what you might think will happen when you consider a black hole, and you can make maybe similar picture here. So this is maybe the space-time. It won't be very, very good without this. So here, so you can think of these as being the space-time when you are very far from the center of the black hole, where here it's almost acts like a drainage for, well, we don't know what will happen if we fall inside, but what we know is that we cannot anymore communicate. It's not really though inside, okay? We all should always think of, understand that this is just the future. So we know that if we, that at least from outside, that if there is an observer that gets there, it will inevitably in the future hit a point, possibly, here in the drainage that we know from the description of gravitational equations that it's a singular point. So this is a singularity in equations of motion of Einstein. I should actually depict it like this, maybe like this. So where since all the mass is concentrated, that means that becomes almost a point, a singular point where it's the mass is extremely high, and therefore the gravitational attraction is also very, very high at that point. So physicists were wondering, how on earth can this happen? I mean, this is all from classical general relativity. And you would say, okay, suppose there is a particle and poses the black hole, we can't get any communication with that. What happens? How can a particle disappear? And if you have this understanding, if you start thinking about entropy, you could say that one or more particles will carry a certain amount of entropy. And when they disappear into the black hole, what happens to their entropy? It should go somewhere. So from this kind of argument, Bekenstein arrived to the fact that the black hole carries entropy. Its entropy of the black hole is proportional to the area of the horizon. This is the place of contention, let's say, okay, over 4 Newton. So from this little description, there are of course other constants that we set to 1 for this unit. So, but once you come to fact, once you come to this understanding, then you have all sorts of other questions. So that means that they carry information. That means that information, once you're behind the horizon, cannot be transferred. You will know it. But most importantly, it means that there should be, in the understanding that we have about entropy, there should be some microscopic constituents that would be responsible for this entropy. Just like when you have the gas. When you have a container full of particles, and the more randomly and highly that they move around, the motion of these constituents will bring about larger entropy for your system. And with entropy, of course, and all this thermodynamic understanding, there comes temperature. And indeed, the question is, do the black holes have temperature? And indeed, the black holes also turn out to actually be characterized by temperature. Note that this is quite different from the way we deal with physics up to, let's say, gravity, when we were looking at the physics of the very, very tiny constituents, even in quantum mechanics or before the classical motions. Temperature was a parameter that would be introduced from us later. We would have our system, ideal system, where, for example, there would be energy conservation or other conserved quantities, and then maybe we would choose to heat it up and see what happens. It's not something that's forced upon us by the theory, which is the case here. So, in reality, the understanding of temperature really, and the fact that the black holes have temperature, comes from the first attempt to marry classical Einstein's theory of general relativity with quantum mechanics. And in a sort of a semi-classical treatment, that's the first thing you would do also when you study particles in a box, for example. Hawking understood that black holes radiate, there's thermal radiation, and they will eventually evaporate, which is also another mystery that goes along with the fact that they have temperature and entropy and all that. So it seemed like from the beginning that it would be very difficult to marry really gravity with quantum mechanics, and that would be like a flaw in the whole story. Something would be, it makes us wonder whether we haven't understood something well. Would you say, why would you have to do that? Because eventually you would like to consider constituents that are very small. Okay? And if you want to have a complete picture of what happened, that's something that you have to do. So you will have to abandon something, or we never actually abandon anything in physics. We change a little bit, or a little bit more, depending on the circumstances, so that everything fits into a consistent picture. And what is that allows us to do that? Constants of motion that can be small or big, depending on the problem, like Planck's constant, where it's almost zero for classical physics, but it's not for time constituents. And the same thing happens here. We have already a constant, that's Newton's constant in the game. So this is how we will try to deal with this problem. So there were, of course, over the years, many ways that people attempted to solve the problem of quantizing gravity, and perhaps the most useful is obviously the embedding of gravity and quantum physics within string theory. And but even beyond that, the one way that we can understand like quantum gravity today is through the holographic correspondence, which is something that came out of string theory but can obviously stand on its own right now. So what does it mean it came out of string theory? String theory is obviously a theory that was proposed in order to unify the fundamental forces of nature, gravity, and those forces that can be described consistently by quantum theories. And through that theory, a multiple of theories that were different expressions, mathematical descriptions rather, of the same one showed up. So that is, let's say, a very, insofar as we are concerned now, what we can use from string theory. So that there were a lot of different theories that were mathematically seemed completely different, that were proven to be descriptions of the same. You could think perhaps like it's a very crude analogy, but you can think perhaps of thermodynamics and statistics. So in thermodynamics, you don't really look inside the macroscopic object. And you can very consistently describe it with the parameters that you have and that you experience in your day-to-day life, which is temperature, entropy, energy, volume, a number of constituents. You don't need to know anything else. But then from classical physics, you have a totally different description. You can think of the particles, the fundamental laws of motion of those particles, and how you marry those with statistics, and they can give rise to exactly the same expression. Okay, so this is perhaps not the best analogy, but it's some kind of analogy to see that this is not something so weird. We often have different mathematical descriptions of the same thing, and different ones are useful in different contexts. So in this context, we are going to describe the way that we understand at least how to deal with gravity from what is called the holographic correspondence. So what does this correspondence tell us? It tells us that we can have a theory of gravity in, let's say, d dimensions. You will obviously prefer to use 4, where this is space-time. Okay, space-time dimensions. So 3, like and you can also describe it in the language of a quantum field theory. So here I didn't say whether gravity is quantum or classical. I start with a classical theory, but this theory can be quantized. I just know its mathematical description, classically, and that is general relativity wise. I don't know how to write it with appropriate variables in using the laws of quantum mechanics, but it exists. Here, I have a quantum field theory. This, we said, is the mathematical description of all matter in the universe. It's a theory that I know how to use. But again, most probably, I know it quantum and classically, but I cannot, in all regimes, solve. Okay, I know more. I know perhaps more of what I'm talking about, but it doesn't necessarily mean that I can always find solutions. Okay. To the problems, to the physical problems of time. So this will be in one-to-one correspondence with a theory like that in d+1 dimensions. And you'll probably want to say that it's more interesting if we can see them in 5 minutes. So this, of course, the way I described it is very general. And it is true that all the details, let's say, of this correspondence have not been worked out in full generality. There is, however, a specific example of a gravity theory and a quantum field theory for which this is exact. Okay? And that is, in principle, a description of quantum gravity. In this kind of language, a description of quantum gravity with parameters that I do not know how to describe here could be given for me from here because of the one-to-one correspondence. So, you probably have heard this many times, or if not, so string theory provides a concrete example of this. Via the AES CFT correspondence. Now, what is the difference here? This is a special example where the gravity theory is a theory that is in anti-de Sitter space, and the quantum field theory is a special theory that has conformal symmetry. Oh, we're almost out of time, so I have to go fast. I'm sorry. Okay, so maybe for those of you now, let's say that have heard some of these things, let's say a few more things. So, more often than not, people discuss this correspondence in terms of d-dimensional boundary of a d+1 dimensional space. And here I will give you one description schematic of ADS space as a cylinder where its boundary is all this surrounding cylinder, and the inside is the bar. So all of this is area space, and the quantum. Oh, I moved it. I hope I wrote it opposite here, so I'm sorry. So how come nobody corrected me here? So the QFT lives in 3 dimensions and gravity is in D+1 dimensions. So here you can have 4-dimensional gravity and a 3-dimensional quantum field theory of the boundary, or 4-dimensional or 5-dimensional gravity and a 4-dimensional quantum field theory of the boundary. So there are many other descriptions of ideas, but this is the one that I'd like you to have in mind. So when we're talking about gravity in de Sitter space, and that's where we'll focus now, and why are we going to focus on this example? Because this example has more symmetry and it's therefore easier to work with, and that is why it actually was explicitly discussed more up to now. So in the context of strict theory, these are of course some specific theories, but right now we understand that to a large extent a lot of these things are true generally. And what do I mean by that? I mean that we can study things here that we look like that. In that sense, I will be answering the question that I discussed at the beginning of seeing gravity as an emergent field. So this already tells us that there is an emergent phenomenon. You can of course go back. You can think of the quantum theory as an emergent from gravity. That would be totally fine. It's just that we don't have a concrete description of that, fully quantum description of that. You have it through this, and that's why it's more natural. Okay? But both are the two sides of the same coin. So what we would like to do now, and that's let's say my research is interested in, is in understanding how to, if this is a one-to-one correspondence, how to map, let's say, phenomena that we know in gravity, to how to find the appropriate variables and describe them in the field theory, or vice versa, from free theory to gravity. But most importantly, it would be interesting to start here with classical gravity. Take a phenomenon like this Shapiro time delay and deflection. We have a phenomenon and we have an equation that general relativity provides for us. At the classical level, I can try to understand how it is described here. What, in a sense, are the appropriate variables that will give me the same result? That in this context, you obviously understand that there is clear notion of space-time, and here maybe not that much. So a lot of things that appear as space-time might be described totally differently. Okay? So how is it? And once I find how is it described in the limit of classical gravity, I will try to change this limit, vary my parameters, and see how it should be described in the limit of quantum gravity, for example. So this is roughly what we are generally trying to do here. And one thing that it's, and maybe I can say a few more words, I don't want to take up too much time.
The room is booked until 8, we're going to run over.
Well, okay. Yeah, thank you. Okay. say then 2-3 more things about the difference here. So let's say we have now a map. Okay, so let's think of objects that we want to map. In quantum field theory, you generally in conformal field theory, you discuss of operators, not really of fields that depend on x, where x is a space-time. They're usually mapped in fields that live in curved space-time in ADS. Okay, so this would be your quantum field, and this would be your operator in conformal field theory. Now, this field corresponds to some particles you have in your gravity theory, and they have some masses, okay? And what does it correspond to? Here it gives, we have a different sort of quantum number, if you would say. This is called conformal dimension. And there is precise relation of how to go from the mass of a particle in QR to the conformal dimension of the associated operator in the conformal field theory. Now, often particles can have some spin. This will correspond to the same spin quantum number here. And then, maybe for those of you that have done a little bit of QFT, studying scattering amplitudes here, would give you information about what is called correlation function. Now, for those of you that don't know, what is a correlation function? It's something that measures how maybe operators at different points are correlated with each other, how do they affect each other. Okay, and usually we denote with this symbol, like expectation value determined. Now, so now there is one more thing, since we're talking about ADS and conformal field theory here, we don't just have Newton's constant, but we have some other parameter, because ADS has space-time, it's a special space-time. Remember, I depicted it as a cylinder. This is because a cylinder in 5 dimensions has spheres as intersections. So these have a radius, and this radius is the radius of ADS. That's how you call it. So there is another parameter of length in the game. So the point is basically these physical parameters, what do they correspond to the conformal field theory side? And in general, for those of you that know some QFT, you know that your theory will have like a coupling constant, a measure of the interaction. And there is, however, here in the type of quantum conformal field theory, so a conformal field theory will have this parameter, will have different parameters that will characterize it, but will be similar to that. So I will just first write it. This is like lambda. This is Hooft coupling constant, and you can think of it as coupling constant. I'll say a few words afterwards. And the other parameter is C, which is say in 5. This is in 5 dimensions. Here is where n is the degrees of freedom. So, the conformal field theory has similar parameters as the general quantum field theory, but they're a little bit different distributed. Now I will tell you a little bit more about that. Not too much because it is beyond scope, but it's important to understand when we have classical gravity here, fixed by these parameters, the radius of the ds is very, very large. What do we have here? Here we take what I called as delta graph to go to infinity and study the theory at large n or large number of degrees of freedom. You might immediately see something here. I'm talking about degrees of freedom, so basically in this description I have a large number of degrees of freedom, so I think you can almost think of something that resembles thermodynamics. So this is large C. Okay. So I don't think you can understand something else right now, but what I can say is I want to tell you a little bit what is the gap here. In this theory, we have a lot of operators. Can you see this graph here? So we have operators and conformal dimensions. So different operators. Which have different operators are characterized by their spin, L, and by conformal dimension. Okay, this fixes the specific theory that I'm looking at. So a given conformal theory has, let's say, some operators of spin delta and conformal dimension L, and this is the analog of these particles. Here we have mass and spin. So the question is, what kind of content this theory has when it's described by classical gravity, and that's what I'm going to tell you now. So it has operators which can have no spin, scalars. We can have spin 1, these are vectors, and there is spin 2. Let's say make them like here. So for some deltas correspond to some deltas and some spin, but it doesn't have any operators. All these other operators. Sorry, I have to make it small. So this is delta gap. But all operators which have higher spin than 2 have conformal dimensions that are much, much higher. So effectively, what am I doing in this way? I'll say it works, but so the conformal dimension, this quantum number here, which is associated to each operator, corresponds to a mass and particle gravity. Here I have operators with 0, 1, and 2 spin. What is a particle associated with spin 2 that you can think of gravity? Gravity. So the graviton has spin 2. Particles that would have higher spin are not in my theory classically, because there is a parameter here in my safety which controls their conformal dimensions and which I send to infinity. So my conformal field theory has all these more and more operators which correspond to particles here, but in the classical limit they are discarded. This is the first approximation, and I didn't forget about them. And I'm making now up a theory that has a smaller set of operators that I can map to particles in my gravitational description. Now, this large n is associated to, so roughly speaking, the large radius radius is this, and the large n is associated to Newton's constant. Okay, so it's another parameter that I cannot write describe. So maybe I'll just say now a punchline for the finish. So having described this, I can now take a general theory. I'm not going to take a specific conformal theory. I'm just taking a generic theory, which has the minimum requirements to have an equivalent classical description like graph. Those theories exist. So they have this kind of spectrum. They have some parameters that I can tune, and they have the spectrum of operators, and they will have a stress energy tensor necessarily. Okay, that will be dual to my graviton field. So this, once I have this, I'll try to compute stuff. So I told you that you can compute in gravity. Now, instead of doing it in flat space, I do it in ABS. I can do the same computation that I do about the Shapiro delay in classical gravity. I can do it in ABS, in classical ABS spacetime. I can find some time delay from a light particle. What do I study? If you know GR, you study geodesics in this background. These are the paths that particles are traveling with the speed of light. These are their trajectories. And you see how they bend in the presence of a heavy object. What could be a heavy object that might be interesting to study? A black hole. So what do? I put classical ABS, Schwarzschild geometry, the black hole, and I'm studying the geodesics. And I'm looking to compute these two quantities. Computationally, it's doable. It's taken a little bit more messy, but you can get a result for these two descriptions. You can repackage this information in the form that I told you before as a phase shift in the wave that travels along this trajectory. And then you try to compute something here. So it turns out that what you can see here is basically the Fourier transform of a correlation function. Now, what is this correlation function? I wrote it in terms of the operators that it contains. These are all in different points. We will consider one at 0 and one at infinity. This is possible to do because we are considering conformal theory. You don't know this, but it doesn't matter. So if you want to draw now the ABS with a black hole, you can think of the black hole sitting in the middle. The heavy state will be at 0 and infinity. Yeah, it's not a good description. Don't worry, I did it. Anyway, so this is a 4-point function, but these two states, these operators are the same, and these two operators are the same. And in reality, what these operators do, they form a state which is like the black hole state. So the black hole state here has a very, very large mass. So I'm going to take an operator which has very, very, very large conformal dimension. What does large mean here? This is like a square. So I'll have to take this to scale with the degrees of freedom of massive T. Now, then it's my background, and I'm interested in how these two interact. This will be like a particle that travels in the background of a black hole in ABS. So it doesn't change the background. It's a very light, very energetic particle. It just feels only the space-time geometry that's different. And so this is precisely this. So that means that you now have like a description that's fully quantum and mechanical, from which you can extract a parameter here that is exactly contains information about the problem. Now, there is an interesting question. What happens if the particle is in a trajectory that will fall into the black hole instead of showing up again on the boundary? We didn't discuss this very well. So what happens if it falls into the black hole? What happens in recent years, we understand that basically what happens is that this correlation function is such that it's evaluated at some time, which is shifted by I pi over 2, that shows up here as well. Maybe I should just say this, that the phase shift is shifted by I pi over 2. Yeah. Delta is shifted by I pi over 2. Okay? And you would say, how on earth are you computing in any quantum field theory correlation functions where the time is not purely real? What would that mean? It turns out this is not a two-point function in a heavy state in one theory, but is a two-point function in a heavy state that correlates, entangles a theory in one CFT with a theory in another CFT. In this case, both of them have real time. It's just that if you shift it, you can describe them both in the same way. So this correlates with the picture that maybe you have seen or you will see. This is what is called a Penrose diagram. And you can see, for example, paths that go from one side to the other. This side is where this is let's say a description of the gravitational theory. It has one boundary here and another boundary here, and these are the light cones. So you see signals can communicate here. You cannot communicate in this region. You cannot go from here to here. But quantum mechanically, these theories that we here can be entangled. And now quantum entanglement, it's something that's very understandable in CFT. You can compute if you know quantum mechanics, you can compute the expectation value. This has a meaning of some sort of communication between two geometrically unrelated areas of space. Okay. So I think I'll leave you here. I hope I try to convey a little bit of what we're doing, and I hope that you might be interested in the future perhaps join us.
Thank you very much again. It's no problem. Does anybody have any questions?
Maybe
Yes.
many questions.
For the Shapiro time delay, it goes as log of the impact parameter. What, I suppose, what moves those work out such that the larger the impact parameter is, the more delay you get? That's really simple, I think, the parameter scattering.
Oh, you mean because I don't know how mine is there, or whatever?
Yeah, you said that there were in particular units that were set.
Yeah, well, now I don't remember exactly what the parameters are stating. I just wrote it so that it's very simple. I mean, the parameters that play a role are in the equation. That's all why I wrote it.
So if you were to take these infinity you still get
Yeah, I basically, okay, in reality I wrote it this way because this result you can take from my limit of anti-de-Sitter impact parameter description, and then there it's just, it's a little bit more complicated result, but it reduces to a lot. The reason that it reduces to a lot is just because of the four-dimensional space. Dimensional space, right? Now the parameters visually that enter there, what kind of distance? You want some distance parameter. Probably that will show up because you don't like that it blows up. And this is, of course, a unit characteristic only for 4 dimensions. But I don't remember now in the flat space. I can look it up and tell you tomorrow.
Any more questions?
That's a very question. Thank you. Yes.
What's the difference between CFT and QFT?
Yes, so you're right. I didn't explain that. I'm sorry. So CFT is a quantitative theory that has an extra C. So it's like your conformal quantitative theory has basically pointer estimates. It has like translations and rotations or Lorentz rotations. When you discuss conformal theory, you have these pointer estimates, so translations and rotations, but you also have some extra things. The most important of those is rescaling. So you can rescale the things and things don't change. The theory doesn't change. And the important, let's say, aspect of that is that in normal quantum theory, things depend on the energy scale that you measure it in, but in conformal theory, they're always the same. Usually people that have a cauliflower is that no matter how much you zoom in the cauliflower, there's a specific cauliflower. I mean, there are two speeds, not the standard one, not the one you work, which has like, it's almost like a triangle or something. No matter how much you zoom in, you see the same picture. So basically, that's what you can have in mind.
So, how does it affect the renormalization problem?
Yeah, so these theories are usually
Well, if there are no more questions, then